And well, at the moment, the more complicated thing is that we have to specify some predicates. So let's have a look at the second exercise here. Assuming we have an atom that says lives in XC, expresses that a person X lives in city C, and the atom same city X and Y expresses that X and Y live in the same city. How would you define same city in terms of lives in? Okay, that's the basic idea. Well, of course, we start like something with lives in. So let's use another window of Klingo. So okay, lives in, and we have a couple of persons. So let's say Caesar is living in Deggendorf, and who else do I know? Andreas lives in Deggendorf, and maybe a third person. And, who else? Maybe Waldemar. No, Waldemar is not living. So Horst, I don't care. Living in Deggendorf. Okay, so this little program, and then let's see here. So there is, well, I already provided something. This says there should be an atom lives in with 2 parameters, and I have to specify a couple of persons who are, well, who are represented by this predicate, and there should be also another predicate which says that somebody is living in the same city than somebody else. Okay, so let's use that one. Same city. And it should be X and Y. And well, we would like to have a definition, so it's colon dash and then something else. So what would we have to do?
I could say lives in like X and C. Goes another lives in Y and C. And
okay. And lives in Y and C, yes. Okay, let's try that one. Looks nice, and it says here Caesar. Okay. So it says that Caesar lives in the same city as Caesar, which is correct. Andreas lives in the same city as Caesar, and Horst and Caesar also in the same city.
Add another thing to avoid Caesar and Caesar. We could add like X not equal Y.
Yes, X unequal Y. Very nice. Yes. What did I do wrong?
The bracket, the extra bracket on the right.
Yes, the extra bracket is not correct. Yes, you're right. Okay, let's see this one. So we have same city, Andreas Horst, Caesar Horst, Horst Andreas. So there's another effect. So we see here Horst is in the same city as Andreas, and Andreas is also in the same city as Horst. So any idea how we could, well, this is okay, of course, since Horst is living in the same city as Andreas, and Andreas in the same city as Horst. So we would not really have to care about that. But maybe this is a little bit more complicated if we just would like to have one of those, I think this is fine. We could say that if somebody is living the same, if X is living in the same city than Y, then also Y is living in the same city than X. This is symmetry. Okay, so I don't care about that. Maybe in another example, we think a little bit more about this one. Okay, fine. Yes, that's the example and how this works. Okay, so you see here, these are not very complicated, but just try the other example on your own. It will help you. There's another one which says, so if we assume that we have persons and that have ages, so there's an atom age X and N expresses that person X is N years old. And then we could also define something like older. So which person is older than the other one? And this would be specified with another kind of definition. Yes, but these are definitions. So so far, well, definitions are not quite complicated. In our example here, this definition is just created by writing another or new rule for ASP programs, but things can be a little bit more complicated. So here, well, there are two more cases. And the two more cases is that we are not able to specify a definition with just one rule. So there may be cases where we have to specify two or more rules, which have to be provided for the overall definition. And in the second case, you might, or it might be necessary that you introduce some auxiliary predicate. So we are going to see this. So we have learned about definitions. Definitions are just rules, but you might have several rules, and you also might have auxiliary rules in order to define something. Okay, so let's have a look at multiple rules. Here is an example about parents. So it could be the case that you just have father and mother defined, and then how is parent defined? So let's have a look at our example, which we have been using before. So let's consider parent Ann Bob. So Ann is the mother of Bob, of course, and Bob is father of Carol, and Bob is father of Dan. Okay, there are these definitions which we already have had. So in order to specify parent, so of course, well, I just copy them, and well, this is not complicated anyway. However, it's interesting to see that. So if we just have a small database specifying mother relationships and father relationships in order to have a parent relationship, we would need to have a rule which says, okay, if X is father of Y, then X is a parent of Y, or parent, well, X is a parent of Y if X is mother of Y. And of course, if I run this program, everything should be the same. So you see here, we have father, and there is the mother predicate. And then we have parent. And we also have the child relationship, which you can see here. And then we also have the grandparent relationship, which you see here. So, well, this is not a big model at all, but as you can see, it starts to create bigger models, even if I just have three definitions here. And just to repeat what we have learned last week. So for example, if you are just interested in grandparent, then you could use a show directive, and we would use grandparent and specify 2. And if we run this one, then we see here grandparent is Anne of Carol and Anne of Dan. But please don't forget, this is not the overall model. It's just that the show directive that presents us just a segment of the overall model, which was created by that. Okay, I hope this is clear so far. And yes, the interesting thing about that is that sometimes we need more than one rule in order to specify a definition, creating a new atom in the model. And here's another example which we can use in the same little program here. And I'm going to add that. So it says we would like to define the relation ancestor, which is which is usually defined as well, a parent is an ancestor, but also an ancestor of an ancestor is an ancestor. And we can have a look at the result here. And as you can see here, we have 5 atoms specifying ancestors. And of course, so Anne is an ancestor of Bob. Let's check that. Anne is an ancestor of Bob, yes. And Bob is an ancestor of Carol. Bob is an ancestor of Carol. Yes, it's here. Bob is an ancestor of Dan. You can see it here. But also the grandmother is an ancestor of the other. So Anne is an ancestor of Dan, and Anne is an ancestor of Carol. Yes. Well, just a little question in addition. This second rule here is clear that we can use it. So it's also a definition which uses 2 rules. So we have 1 rule and we need a second rule. And the second rule, it has another property. It's defined recursively. So it says, if you have an ancestor, X is an ancestor of Y and Y is an ancestor of Z, then X is an ancestor of Z. So that's the idea about this one. Just a little question about this last rule here. So you could specify this second rule differently. Any idea about that?
We can use the parent 2 times.
Yes, you're right. We can use the parent. So, well, the interesting thing about these things, if you specify rules like this, then it quite often helps if you think about the relationship which you would like to represent, which is a relationship of the real life, and then just try to formulate it in plain words. So we know that somebody is an ancestor of somebody else. If we have an ancestor of the somebody with a third person, and the third person that has a parent which is also then an ancestor. So the idea about this is we could specify that X is an ancestor of that if X is a parent of Y and Y is an ancestor of Z, or even the other way around, if X is an ancestor of Y and Y is a parent of Z. So everything works, and we can just try this. So we could have specified something like parent and then ancestor. Of course, we cannot replace the second occurrence of ancestor here, and this will result in the same model. Okay, yes, fine. But that's part of the logic, and well, we have learned a couple of things. It helps to think about the rules as you would like to specify them. Okay, so far about the second part of definitions. Let's see here. Yeah, it's just a question, what models will this produce? We already have seen that. So I just showed you the result of the Klingo program, which is a question about this exercise here. Okay, our final part about definitions. As you remember, so definitions, what have we learned so far? Definition can be quite simple. It's just a rule, like we define child in terms of parents. Definitions can become more complicated if we need more than one rule. So a parent is a father, or a parent is a mother. We define some new predicate in terms of another one, but we need more than one rule. And here's the third type of definition we use. So we define something which is called composite, and we use an auxiliary parameter. Oh, no, sorry, the other way around. We would like to define prime numbers. Okay, so this little program gets a little bit more complicated. We define prime numbers, and we define prime numbers based on another auxiliary predicate, which is composite. The basic idea about that is quite simple. So the composite predicate just enumerates numbers which are multiplied by some other numbers. So let's have a look at this predicate here. And well, it uses a couple of things we have seen before. So here is an interval. As you remember, it was in the last lecture. And there's another interval, which is also from the last lecture. And there is a little bit of arithmetic. So here is a minus, and there is the modulo operation, which is the integer division with no sorry, with no residuals. So there is nothing left over if we divide this. Okay, so let's have a look at this composite predicate, and we also need a little bit more about this one. Okay, so yes, we can use this instance of Klingo, and I could try to run this little program in order to see what it does, and we get an error here, and it says that the interval is undefined. Okay, this was obviously by purpose, and there's an interval specified that n is varying from 1 to u. So what about this u? What is it? Any idea about that one? So what is the mistake about that one? Well, it's just a little bit about basic rule syntax. So you remember we can have 3 types of terms as far as we have been seeing them so far. So this term here is a variable which appears here in the in this interval atom, and then we have another variable which is the big I, which appears in another atom, which is also an interval here. And then we also have the n and I. Okay, we also have another term. So we have a numeric constant, or we have 3 numeric constants. So there's numeric constant 1, there's numeric constant 2, and another numeric constant 0. Okay, so what about du? Okay, u is a symbolic constant, but this u is not defined so far. And well, in order to have this program running, we have to define the u. But we could do something different, like, for example, we could just replace it by, I don't know, 20. So if we replace this by 20, then we have an interval that n is out of the range from 1 to 20. and I is from another range. Okay, so let's just try this one. And you see here, we get a running program. But this is not what I would like to show here. So let's talk about the U and what can we do. So this is some kind of repetition of last week's lesson. So a good idea about this U is that we specify a constant. And you remember, though this is another directive which says constant U is 20. And we need a dot in the end, or maybe I use something different here. Maybe something like 12. Okay, so let's run it and then let's have a look at this rule because this is kind of a little bit tricky here. So if we do this, then we see here we get composite atoms and we get 6 of them. So we see that the number 4 is a composite, the number 6 is a composite, the number 8 is a composite, 9 is a composite, 10 and 12. Well, that's the basic idea about composite. We would like to have all those numbers which can be created by multiplying 2 numbers. So you remember 4 is 2 times 2, 6 is 2 times 3, 8 is 2 times 4, or 2 times 2 times 2 times something like 10 is 2 times 5, and 12 is 3 times 4, and 9 is 3 times 3, of course. Yes. So these are all composite numbers. You probably would have expected something different here. But there is this this modulo division. And well, it says, so we have these numbers from 1 to U, which is 12 here. And next E is from out of the interval from 2 to n minus 1. We are going to have a look at that. And then n should be a composite if n divided by y has no residuum. So there is no rest of the integer division. Okay, well, that's it. How could we try to figure out what this rule is doing? Any idea about that one? So, but yes, you can think about this and say, okay, yes, fine. Says everything, or it's a correct specification. However, it would be interesting to specify things a little bit different. Okay, so, and also this is kind of a repetition of our last lectures. So the first idea, well, if you would like to figure out how this program is working and how this rule influences the result of our model here, then a good idea is to create instances of this rule. So we could create a couple of instances, so maybe something like that one. I can always add copies of that. So this does not really change that. So, well, there are rules and the rules say the same thing. The ideas about instances is that we try to figure out what's happening with the interval. So a first instance of this rule is that we just use 1 here. So it says the rule says from 1 to 12. So that was our constant which we have been specifying. And of course, 1 is a part of that interval. And how can we instantiate furthermore? So it says n is equal to 1. So of course we can replace the n by 1. And let's do the instantiation. So it says we have here 1 by 1, and then the composite 1, and we obviously have to replace this n and this n. Then we see here, I is out of the interval from 2 to 1 minus 1. So it's from 2 to 0, which is then, for example, well, so we can have a like the 2 of them, and if we instantiate furthermore, we will get something like that. And so here is the division 1 by 2. So if we divide 1 by 2, what is the result by integer division? So if it just if it would have said 1 divided by 2, so what's the result of 1 divided by 2?
0.
Yes, if it's an integer division. Of course, 1 divided by 2 would be 0.5. But since we only have integer division in answer set programming, you're right, it's 0. But we are the other way around. If we divide 1 by 2, then we have 0 and is the rest of the division.
So will be 1?
Yes, it will be 1. But this comparison says that 1 divided by 2 has to be 0, which is obviously not the case. So this one is false. Yes? Because if we instantiate it like this, it would say, well, it would be 1. So this one is 1. So let's replace that one. And now the rule says composite 1 would be in the resulting model if 1 is 1, which is okay, if 2 is 2, which is okay, and if 1 is 0. But this is not the case because these are two different numbers. So composite 1 will not be in the model. So that's the idea about that. So there's a rule which is okay for the program, but this will not result in any contribution to the model. Okay, so we could continue and try something like, so let's take the next rule. So we had something like n being 2, but well, let's try something different. Maybe let's try something n is 5, which would be out of the interval. So we are running from 1 to 12, and 5 is part of that interval. So if we do instantiation again, then obviously we would have to replace n by 5, which we could do. So let's try that one. And then, so we have the second interval here, which says it's from 2 to 4. Since this one is 4. Then we can just use, well, something like, oh, I did a mistake. Well, no, I did no mistake. I was looking about the 5. And so here in this case, this rule would result in 3 copies. So we would have to use these 3 copies. So there's a first copy which says I is 2, and this one is 3, and then we have 4. And in all these 3 cases, we would replace I by 2 and I by 3. Oh, let's try that one, 3. And I by 4. Okay, so let's check those here. So 5 integer division by 2 is 2.5. So this would result in well, there's a rest, which is 1, of course. And if we divide 5 by 3, then we would have something like 2 here, and this would be 5 by 1. I think it's 1. And so in any of these cases, we just have incorrect comparisons here. So even 5 is not part of the model here. Okay, so let's try one which is working. So maybe the 6th one. So it would be an instantiation like that one. So we have to replace n by 6. So there's one, and the next one, 6. And well, this one can be replaced by 5. And then we have, well, 4 more copies from 2 to 5. And next we can replace the I in the rule. 3, 4, and 5. So if we now think about the integer division, so this one is interesting because if you divide 6 by 2, then well, the result is we get 2 and there's no rest. So this will result in 0 is 0. And the same here. So if you divide it by 3, then we also get a rest. But if you use this one, then should result in 2, and this one, it should result in 1. So these 2 copies, they don't contribute to our model, but these 2 copies, they do contribute to a model, and they create the composite 6. So that's the reason why this is included in our resulting model. Okay, so, well, this was in order to give you an idea about how can we figure out what is happening here. But the better idea is to think a little bit more about those atoms or those intervals which are specified. So in the first case, we say, well, we would do something like we would like to multiply numbers. So there are, well, we start from the interval from 1 to 12, and we would like to do something like 1 by 1, 1 by 2, 1 by 3, 2 by 3, and so on. And this is what the rule here specifies in principle, but in a little bit more tricky way. And in order to do this, we specify the interval from 1 to 12, and then we need a second number, which is starting from 2, and well, we use the part of the first interval to restrict the second one in order to not create so many things. We could also have done it in a different way. So you could also have specified u. So we are just using 2 intervals from 1 to u and 1 to u, and then do the division. And well, the modulo division just gives us if we can divide one by the other, and there's no rest or no residuum. And that's the idea about the composite program. Well, you probably, well, this could be another kind of exercise. You could try to do it in a different way by specifying the times thing. Maybe I'm going to integrate that in another exercise sheet. Okay, so questions about this composite predicate so far. It was just kind of repetition of what we have seen in the last courses. So there are intervals, and we have had a constant, and we have got an arithmetic, and we also have got a minus sign here. Everything works fine, and this just creates what we see here. And we could specify larger numbers. So that's the idea about the constant here. So if we would like to see the composites from 1 to 1,000, okay, I did something wrong. Yes, there is a mistake, and I need the U here. Okay, if we run that one, then you see here the model is growing bigger and bigger, and there's a big composite which is 961. And you can also specify even larger numbers. Let's see here. So if you do that, then the runtime will slightly increase. So, oh yes, it says 7 seconds, and I'm reducing this a little bit again. So let's talk about 20 of them. Okay. So back to our original example. Well, we have a definition here. We would like to see prime numbers. And obviously, I have to emphasize that this is not really a very efficient program to calculate prime numbers. Prime numbers in computer science and mathematics, they are a very, very tricky thing, and the science creating them, or the science searching for the next prime number, is quite a mathematical issue, and you wouldn't in no case try to calculate these things in the way we are doing that. Nevertheless, as you can see here, so it's a very, very simple program, and it just specifies things. So we have a predicate composite, and then we say, okay, prime numbers are those numbers from 2 to u which are not composite. So that's what the rule specifies. And this is very, very simple, and it just uses a definition of prime numbers. And I'm going to use this definition in our little program, and we add it here. And well, is there a question about the rule in line number 3? It should be quite obvious. So it says any number n is a prime number if n is from the interval from 2 to u, and if it's not a composite number, well, which is calculated by the other auxiliary rule. And if we just run this one, then we see here prime numbers saying, so 2 is a prime number, 3, and so on until 19. And obviously, we could, again, specify a show predicate in order to show us just the prime numbers and not the auxiliary predicate. Okay, maybe I just focus a little bit on the not operator here. So as you remember, we have been talking about this one in the week before. I think it was last week. What does this mean? So it says we vary our n in an interval from 2 to 20. So n is any number like 2, 3, and so on, like 20. And so a prime number is only included in the model if there is not a composite predicate included in the model. So in order to understand this even, well, I think this should be clear. Nevertheless, in order to figure this out, you can again use the little trick about instantiation. So if we have an interval from 2 to 20, then we could start by 2, and next would be 3, of course, and then that would be 4, and something like until 20. Okay, so if we instantiate n by 2, so there are more rules, of course. I just now in order to do this, more instantiations. Okay, yeah, it should be correct. Okay, so let's have a look at those rules. So it says n equals 2, and of course we can instantiate n by 2, which we are doing right now. And then we have a rule, it says 2 is prime if 2 is equal to 2, which is the case, and the composite does not includes not the 2. So if you look at the composite here, you can see that, and there is no composite 2 included in our model. And this is the reason why prime 2 is included here. So the not refers to the model. And since it's not in the model, then prime will be in the model. And as we can see here, prime 2 is included in our model. Okay, let's have a look at the next one. It says n equals to 3, and of course we can instantiate 3. And it says prime 3 is included, so you can see here it is included. If 3 is 3, which is the case, and if composite 3 is not included in the model, and if you have a look at the composite predicates here, there is no 3 included here. Okay, so far, wonderful. So next rule, it says if n is 4, so we can instantiate n by 4, or we instantiate while we do this, and it says prime 4 is included in our model if 4 is 4, and composite 4 is not included in our model. However, sorry for that, composite 4 is in our model. Therefore, prime 4 is not in our model. So as you can see, so there's prime 3 and prime 5. You cannot rely on the order of the predicates here. However, they are in an ordered way specified. So that's the reason. So the rule in line number 7, that's the reason why there is no prime 4, because this one is false, since composite 4 is already there, and therefore prime 4 is not included in our model. And of course, we can go on with the next copy and instantiation and so on until we come up with 2 of them. Okay, so that's the program. Any questions about this one? I hope that the not predicate became a little bit more clear in this case. So we refer to the model which was created by the definition in line number 2. The definition in line number 2, it refers in a negative way to the composite predicate. And this is a negation, and there's another form of negation. I'm talking about negation later on, but this type of negation is called, sorry for that. This type of negation is called the negation as failure. And it says the negation as failure, the meaning is, so we refer to our model, and if something is not in our model, then it's a negative, so the truth value of that is negative. Okay, so another type of definition, and well, I presented this example in a little bit more detail in order to talk about intervals and things like that, which you have been talking about last weekend, to repeat those things. Okay, so this was about definitions. So definitions can be very, very simple, like just one rule. Definitions can be multiple rules, as we have seen here. And definitions can be with auxiliary brackets. So we would like to define prime, and we would like in order to do this, we specify another predicate like composite, and we are using this auxiliary predicate in order to instantiate prime. And well, this is the kind of definitions which are a bit more complicated than the others we have been seeing before. Okay, so there are a couple of more examples here, or more exercises here. I'm not going into a detail, so you could try to do this exercise, which is another one about numbers. Well, yes, I would like to skip this one. Maybe I'm going to talk about that later. So it's an example about number puzzles. And this example, well, this is taken from the Lifshitz book, like the other one as well. But I talk a little bit about this one. So in mathematics, there is a rule that every non-negative integer can be represented as sum of 4 complete squares. So, and there are 2 examples saying that, for example, you can create 7 if you have 2 square or square of 2, square of 1, square of 1, square of 1, and add them. Or you can represent 10 by having 4 squares, so 3 and 1 and 0 and 0. Okay, so that's the idea about that one. So try to represent this in an ASP program, that these things are able or are possible to do. The question here is if this is also possible with 3 complete squares. So can we remove 1 square here and try to figure out whether non-negative integers like these one, they can be constructed out of 3 complete squares? Well, that's the question here. So how could we do this? And in order to achieve this one, a good idea is to start out not right with the ASP program, but in order to think a little bit about what I would like to achieve. And you could start to create something like a schema which represents the way you would like to specify those things. So, for example, here, the first 2 lines specify the problem. So we would like to specify if numbers can be created out of 3 complete squares. So the next one, which we need, is we need a positive integer n. So we needed something like a constant. Yeah. You have seen in our example before, we created the directive constant u is equal to 20 for our prime number program. So of course we need something here. And if you start out with this program, so the idea is you could use this. Well, this is a kind of programming skeleton. So you could start to use this. I need some more spaces here, something like that. And it would look something like this one. And you can fill in things. So the first probably would be something like constant n is equal to, I don't know, 20. Let's use that again. And then, well, more things are specified. So it says we need some, well, you can think about that. I don't want to show this right now. But the idea is to think about the problem and then to think, so what parts do I need? So in this case, we would like to have a predicate saying 3. So these are the numbers that can be created by 3 complete squares. Next, we would like to specify another predicate that says then we need something more than 3. And you see here, so there's a specification. What does this mean? Okay, so this is just an idea how to progress if you have a problem at hand and you are not clear from the start how this could be done. And you can just do this by writing down commands and try to fill out this little example. And just try to do this. So it's not a very complicated example, but you could use this skeleton in order to fill in the program. Yes, and there is a final exercise here. There is another one which you could have a look at. So let's see. I've got half an hour left. Yes, I would like to continue and start with choice rules. Okay, so we have been, what did we do so far? It's just our roadmap here again. So we learned a little bit about answer-side programming principle and how rules look and some very basic syntax. We have been talking about abbreviations like pooling and intervals, and we have been talking about arithmetic, which could be used in terms. And the next section was about definitions. So definitions can be very simple, but even a little bit more complicated. Okay, now, unfortunately, it's, well, we come up with the next concept in answer-side programming, and this is choice rules, and this is a little bit, well, in my experience, this is the concept which is a kind of a challenge to understand. Before we start with choice rules, so answer-side programs can have different answers. That's what you have seen so far. So in our examples here, let's have a look at that one. So if I remove this directive, then you see here there is a model. And what the particular case here is, we have got one model and it says satisfiable. So the specified theory is true and it returns a result. However, this might not always be the case. So Klingo may answer us in 3 different ways. So this is quite important. So Klingo can result in, well, the example we saw right now, it was just one model. So it says it's satisfiable and it's true. And there is one model and the model is this one. So this is what we have seen here. However, you may sometimes have a program which is inconsistent. And then Klingo would answer with no. And the most simple example which is inconsistent, so let's have a new instantiation of that. Task.org and run Klingo, and we could specify false. And run that one. And then you see here, Klingo answers us and says, this is unsatisfiable and this has no model. So this is important. There is no model at all. In contrast to this one, it says, so we have one answer and there is one model and the model is this one. And well, maybe sometimes we can specify things in a different way and it will result in some inconsistent behavior, and then Klingo would answer this unsatisfiable. Okay, so this is about the principle thing about ASP programs. And there is a third possibility, namely an ASP program may not have just one model, it may have many models. Okay, so how does this look like? And this is what choice rules generate. Choice rules are not the only way to generate these kind of multiple models, or if you have several stable models, but it's the it's the basic way in order to generate those. And here's a little example. It's choice rules are specified using curly braces, like we see here, and the idea is that we would like to represent some kind of mathematical set. And this says, so we have a set consisting of PA or PQ. And as you remember from mathematics, so a set like this says, so there can be PA and there can be QB, and there can be both of them and there can be none of them. So let's just have a look what Klingo creates from this little choice rule. So we create a choice rule and we run that one. And if I do this one, it says, though this is satisfiable, it has an answer, and the answer is the empty set. So this is important. So there's an empty line. But the more interesting part here is there are more models. So it's not just one model. So in contrast to what we have seen before, so you remember in our case here, it says it has exactly one model. So there's nothing else happening. But in our case here, we have more models. And in order to see those, you have to change the reasoning mode here and switch to enumerate all, which we will be doing in the future quite frequently because we are interested in multiple models. If we run this one, then you can see here the result is, well, it's satisfiable. So Klingo answers, yes, this theory is okay. So it's a valid theory. And we have 4 models of that. And the models are enumerated. So answer number 1 is the empty model. Answer number 2 is the model containing QB. And answer number 3 is the model containing PA. And answer number 4 is the model containing PA and QB. I've been always talking about that we can just remove those parameters, and we could do this here in the same way, and we will get just the same thing. So you see here we have the empty model, and we have the model containing Q, and the model containing P and Q. Okay. So that's the idea about choice rules. Even not very complicated, as a basic part. So we can just add more things here. I could specify something like R. Maybe I also use a number 2, which is also possible. So it says we have the set of those atoms, and there's an atom PA and QB and R2. And the semicolon, it says that they are included in the set, and they are included with OR. So you may have 1 of them, you may have 2 of them, or you may have all 3 of them. So if we run this one, you see here we get 8 models. So models is 8. And then we have answers. So there's another one. There's only one with the empty model. And there are models with just 1 element. And there are 3 models with 2 elements. And there's a single model with all 3 elements. So these are the various models which are created by choice rules like this one. Yes. Just a second, I have to turn on a light in my room here. Okay, I'm back. Okay, fine. So these are choice rules, and that's what I already have showed you in our little example using Klingo. And well, you can specify more things like that. So here in this case, it just uses pooling and interval abbreviations together with choice rules. So like this one here, it specifies 1, 2, 3, and this one uses pooling. So this is not very not very interesting. So we can just use that one, and it will return the same thing here. So this is just PA, PP, PC, and of course we get again 8 different models. Or if we use a pooling statement, something like 1, 2, 3, then it will return in the same thing. And you remember you can use pooling with symbolic constants, and you can use an interval with numeric constants. And of course, we could use some bigger numbers here. If you do that, then you see here we get quite a lot of models. And so you see here it creates 1024 models. And the biggest model is this one, including all those P predicates. Okay, so this is just an addition to what we have seen before. There are more exercises, and I would really like to leave them to you. Please try them and try to figure out what's happening here. Like this one. Oh, maybe let's have a look at just one, which is this little program. Sorry, I have to go up. Okay, before I run that, let's think a little bit about it. So what does rule in line number 1 contribute? So if we just have that one, what would we expect in our model? So how many models would we see here if you use just that one? Well, it will result in 2 models. So it may be the empty set and it may be the P. Running this one, okay, you see it's the empty set or it's a P. So if we add the second rule, if we would have just this one, it would result in also 2 models, the empty set and this one. So if we have both of these, what would we expect?
Probably 4 models.
Yes, probably 4 models. I would also think so, because this one creates the empty set in P, and if we add the next one, if it contributes the empty set, then there's nothing new. Then, but we have 2 models again, and this contributes the P, and so we have it's just the 4 models we have seen before. So this little program is similar to the other program which is here. So these 2 programs, they are identical. But well, I would like to try those examples and think about it, and what do these things mean? Before, well, I would like to talk about an exercise sheet. However, I integrate. Well, let's talk about these two slides. Again, so choice rules can be augmented with numbers. You can see this one here. So remember, this was a basic choice rule as we have seen it before. And we could specify something like two numbers, one before the choice rule and the other one in the end of the choice rule. And it specifies lower and upper bounds. And the meaning is we would like to restrict the models this one creates. So there is a set consisting of a number here. In this case, just, well, we have 3, but this might be even more. And the lower bound says we would like to have at least one element in the answer. So any answer which has less than one element, this is not an answer to this program. So this is what the lower bound meaning is. And the second one, it's an upper bound, and it says we would like to see only answers that have 2 elements of this choice rule in maximum, and more of those 2 they are not allowed. So let's have a look at this little program. And this is quite easy, and you can see this very easily from this little example. So you remember, this is a choice rule. We have an interval from 1 to 3 in P, and of course, it's like we have seen before, it creates 8 models. So we have the model with an empty set, and we have a model with 3 and with 2 elements and so on. So if we specify a lower bound, something like 1, well, let's do the example as we have seen here. So we would only like to see models which have 1 element in minimum, or 1 atom in minimum, and 2 atoms in maximum from this choice rule. So not from another rule which might be there. So we would like to exclude answer 1, which is the empty set. So this is not allowed. And we would also like to exclude answer 8, because this has 3 atoms in our model. And if you do this, then you see here, we get 6 models, and those 2 are not included. So you can play around a little bit more with that one. So if we say we have a lower bound 1, so we would like to have at least 1 element, but we don't care about an upper bound. And of course, we get the answer number 7, which is all 3 of them. Or we could like to specify that we would like to have at least 2 predicate there. And then you see here, we have, well, 2 or 3 of them, but not 1 and 0. And of course, you could also do this with the upper bound. So if you specify an upper bound like 3, no, 3 is all of them, so 2, then we have 7 of them. So it excludes the answer with the 3 elements, but you could also say, I would like to have just 1, and then you get P2, P3, P1, and you could also specify the 0, and then, well, you see, it's still satisfiable because it's a set, and the set creates an empty set. So it's just 1, and this empty set is what we get here. Okay, so these are boundaries which could be specified with choice rules, and they restrict the number of models which are created by the choice rule. Yes, and a final slide about this one is, well, I just use this little rule, and So it's just a choice rule. And of course, so in this case, it's a pooling statement. You see here we have symbolic constants, and there are 6 people specified here. You recognize this by the names. And of course, you could specify something like 2 as a lower bound and 3 as an upper bound. And things would happen similarly to what we have seen before. Okay, so these are 15. And the basic idea about that one is, just add some semantics to that. So if you think about Anne, Bob, Carol, Dan, Elaine, and Fred, so this is a little club, and this little club likes to elect some kind of committee or representatives. And you would say, so when we elect people from them, we would like to have a committee consisting of 3 different persons. And you say we would like to have in minimum 3 persons, and we would like to have in maximum 3 persons. So if I use that one, then you can see here, so we get 20 models. And so this is any combination of persons out of those 6 persons. So it's Fred, Elaine, Carol is one possibility for this committee, Fred, Elaine, and Bob, and so on. So you have 20 possibilities. And this sometimes happens that you have a lower bound and an upper bound, which is the same. And there is another abbreviation you could use. So if you have the same upper and lower bound, you can just specify something like the choice rule is equal to 3, and this would result in the same answer. Or we could specify. So, for example, if they would like to elect a boss, so this would be just one person. And then you see here, there are just 6 possibilities how they could elect a boss. And this equal sign, well, it's just a syntactic variable, just a syntactic variant of specifying 1 in the beginning and 1 in the end, something like this one, resulting in the same set of answers. And you could also specify it in front of the choice rule, not in the end. And this is the same thing here. So far about choice rules. So that's what I wanted to present. So we have, well, the basic idea. No, it's just about choice rules. Choice rules, they can create a lot of different models, which makes it complicated to understand or to understand what we specify. But choice rules look quite similar. So we have this representation as a set with some members, and you can use pooling and intervals as abbreviations, and you can specify an upper and a lower bound, and the upper and lower bound may be also specified with an equal sign if the upper and the lower bound is the same. So that's about choice rules, and I would like to motivate you that you try these little examples about choice rules, and we go into choice rules in the next lesson. So I've got 7 minutes left, and I would like to use these 7 minutes to show you another thing. So I have, well, this is our iLearn system, and this is the representation of the course. And there is a new sheet to use for practice. And so if you have a look at that, then you can see here an exercise sheet, which is represented here, and there are a number of different little problems which you should try to solve. And in order to think a little bit about that, so there are examples which look not very simple at the first sight, but you have to try to figure out what you have to do. For example, it says write a Klingo program that represents the following features. So there are 10 persons known by their respective names. So what could you do about that? You have to specify a predicate. You have to get an idea how to formalize this in terms of ASP. And just to give you a little hint here, you could say, so there is a person N, person Bob, person, and so on, and you could specify 10 of those. And then there's some additional statement. So some of these persons are friends. So how could you specify this one? So friend and Bob, something like that. And there are more things. And well, this exercise, this is just to that you try to find possibilities to model things in terms of predicates and in terms of logic, in terms what you can specify for an ASP program. And this is obviously the same if you consider the part of Cesar Ionesco's part of the lecture. A little bit more I have to specify is about this little example. It considers the trees and tents puzzle. So I have to explain a little bit more about this one. Okay. Maybe. Ah, I was wrong, so I have to use that one. Yes. I would like to introduce the trees and tents puzzle. So this is a little puzzle. I'm coming back to that one, and we could try to solve this one. So what about this little puzzle? So in order to understand that, so there are, I already provided a couple of links here, though they are in the introduction slides, and you can have a look at that one. So if you check this, so okay, this is a German. Okay, yes, there's no English representation for that, unfortunately, but maybe we use the other one. There is an English representation. Yes, here we are. So sorry for that one. Yes, it specifies the rules in English terms, and you can also use examples of that. Okay, so back to this little puzzle. So the idea about the puzzle is that you have a kind of campsite, like, well, it's not a European type of campsite, it's more an American campsite. As you, if you ever have been at such a place, then you know that they like to separate tents from each other. So there are, well, you see here a campsite, and it's a square of 8 times 8 locations. And on some of the locations, there are trees. So you see here, there's a tree on the position. So if you just count them, so this is position 1, 1. then on 1, 2, there's a tree, and on 1, 6, there's also a tree. On 2, 1 is a tree, and 2, 2 is a tree, and so on. The idea is you have to fill in, or you have to place tents. So the idea is there are a couple of people coming to your campground, and you have to place them. But there's a rule. You can place a tent only next to a tree. And you can place tents on the campground only as many as there are trees. So if you see here, there are 3, 5, 8, 12 trees. So you can just place 12 tents on it. And you have to specify, well, you have to place a tent, and each tent has to be directly next to a tree. So in horizontal or in vertical mode. So for example, at that place, this is not possible for a tent, but you can place a tent here. So then it would be, on a vertical place to this tree. And there's another rule that tents may not sit next to each other. So if you place a tent here on this place, then you are not allowed to place another tent here. And a third rule, the numbers in the columns and the row on top and the color on the left-hand side, they specify how many tents there will be in the row, and you have to find a solution. So in order to do that, we can just look at a very little example here. So maybe we start with that one. And you can try to find out where to place those tents. And well, you can specify that, but that would be obviously a mistake because it says that in this row there is nothing. So maybe we just place. So in this row we have to place 4 of them. So I would try to place one here. I would try to place one there. This is okay because they are in horizontal or vertical contact to a tree. And I would not be allowed to place another tent here and another tent here because they are next to another tent. And in order to place 2 more tents, I would have to specify them here and there because there are trees. And this is how you try to figure out. So for example, with this tent, we know that there is no other tent in row number 2. There is another tent in row number 3. Okay, where could this be? So I could try to place one here, but this is not allowed because this is next to this tent and this tent. So that's not possible. There is only just one place where we can set up a tent, and it's next to this tree here. So let's try to figure out. So there have to be 3 here. So we have to place one there, and there should be one here and there. I don't know. So maybe, I don't know if there is one here. I cannot place one there. I would have to place one here. No, that's not the case. So let's do that one. And I have to place a third one here. So 1, 1, 1, 1, and 3 of them. Maybe yes. So that's a solution to this problem. And that's the basic idea about trees and tents. So look up the introductory slides, go to the website, try those kind of puzzles yourself. If you would like, there are apps on Android or iOS for the trees and tents puzzle. You could get them and try to get an idea about that. And well, the idea about the exercise sheet. So where is it? So I would like to talk in future exercise sheets about these kind of puzzles. So this here is very, very basic. So you're asked to set up a campground 6x6, and you should place a tent on each of the grid positions. So which is not, of course, valid with the rules of the trees and tents puzzle, but it's just an introductory idea how you could tackle this kind of puzzles. And in the end, I would like to have a solution to the trees and tent puzzles, and we could talk about this. So this is, well, in order to understand this exercise number 2, you have to refer to the trees and tents puzzle as it is specified in the introductory slides. And maybe just a couple of words about the last exercise. So the idea here is, so this could be another example. We could try to set up an ASP program which configures bicycles. You know that bicycle configuration, you cannot combine anything with modern bicycles. Like having, well, of course, modern bicycles combine quite a lot of things. Like you have an E-type drive, and you have a small wheel in the back side and a big wheel in the front side, and things like that. But usually you have bikes which are more like trekking bikes,